I tried the tablecloth trick again. So still don't know where my usual stuff is, but what I've got is a bowl with coins in it. I've got a glass of water, and I've got a light bulb and a cup of pins. So if this doesn't work, then I'm going to have a nice mess here to clean up involving electricity, coins, pens, and water. Okay, so when you want to do this, you got to do it fast. So I hope everybody's back from break. And okay, so let's try this. Okay, so you got to yank real fast with conviction. All right. Let's hope I have conviction. Okay, so if you believe in physics, then the tablecloth trick will work. Okay, and you want to use a small piece of cloth usually so you can get it going pretty fast. Smooth cloth, of course, helps. Silk is better than cotton, but I'm using cotton. Okay, so ready. And 1, 2, I may do it on 3, I'm not sure yet. Takes conviction. Okay, and ready. 1, 2, 3. Oh God, I didn't get it all the way out. Okay, so see, that didn't pull back far enough. Oh boy. But you saw that things did not move much. Let's try it again. Get it all the way out this time. A little bit crowded here. Okay, guys, everybody move together. Also got some wrinkles on the end of this cloth, which probably aren't helping. Okay, try it again. Ready? 1, 2, and 3. Ta-da! Okay, so it worked. You saw that things hardly moved at all. Didn't get a spill from the water, the coins, or the pins, and the light bulb is still working. Okay, so tablecloth trick worked. Okay, let's go look at the worksheet then. I hope you guys were watching. You weren't still off on your break, were you? Did you see watching? Something along those lines. Oh, okay. Thank you, Muhammad. All right. So don't forget to try it at home. But, practice with a few things, maybe without water first. Okay, so let's go look at the worksheet. And I guess bring my camera back. Oops. Not that you necessarily have to see me. There we go. Unpin me. All right. Now I've got people, and everybody's got a picture in. Well, not quite. So, Muhammad, put your picture in. Mahmoud. Marina. Morgan, put something in. See, we got nice flowers here from Hector. That's pretty. Not flowers, leaves. Natalie. Sashik. Okay, don't forget the way to do that is to go to oops, wrong one, not Blackboard. By the way, this picture is showing Newton's second law. Well, actually Newton's third law and second law, but third law mostly. Action, reaction, which we're going to talk about. So he pushes backwards on the turntable there, and he goes forward. So this old-fashioned merry-go-round, which if you've never gotten to play on one, I'm sorry. There is one at Fermilab still, an old-fashioned merry-go-round. in the village, which is where the physicists stay. And so anyway, but they're great fun. But there aren't very many of them around because they can also be a little bit dangerous. Okay, so anyway, so to put your picture in, and there's a rocket car. And a crazy guy. Okay, so anyway, don't forget to change it to go into your, where your name is, change your profile. Okay, so put some sort of picture there instead of a letter, although letters are nice too. But okay, let's go look at that worksheet. So where would we turn this in for extra credit? Okay, so under assignments, there's a extra credit drop box. And so worksheets extra credit. So you drop it into this one, and you can just toss it in. So if you do 10 of them, just toss them all in there. All right. And okay, so let's look at this thing. So what we've got here is a page where you have to do the right side before you do the left side. Okay, so that's one of the problems with this page. Right side, then left side. The right side is all about acceleration, calculating the acceleration for Bronco, the name of this guy, as he skydives down, and then he pulls his parachute. And what they're giving you is you've got numerous points along the way. So there's A, B, C, D, etc., where they're giving you the air resistance and the weight. So these two belong to point A, and these two belong to point B, and so on. So they give you air resistance R and weight. And so they're doing just what we were doing a minute ago, which is why this is a good one to do right now. Let's see what would happen if can I make it bigger? Yes. Okay, so what you're going to do is go along and figure out all the air resistances. So let's do the first one. And so we've got the formula is over here. So the first one, the weight minus the air resistance. So first one, the acceleration is going to be the weight, which is 1,000, minus the air resistance, which is just 0. And then you divide by the mass, and the mass is over here where it says Bronco's mass is 100 kilograms. So his weight is always 1,000 newtons. And so 1,000 divided by 100 is just going to be 10 meters per second squared. And that makes sense, right? When he first falls, he doesn't have any air resistance. So he's going to fall as if he's in free fall. So air resistance takes time to build up. And okay, so the second one, now his air resistance is 400, right? So you would go 1,000 minus 400, divide by 100. So you get 600 divided by 100, right? And that would leave you with 6. Right? 600 divided by 100. Okay, so the idea is that you go down and you figure out the air resistance for each one of these. And some of them are going to come out negative because when he pulls his parachute, all of a sudden the air resistance is greater than the weight. Okay, so you go down and you figure out the air resistance each time. And then we're going to go over and answer these questions. So let's do a few more. Can someone give me the air resistance, the acceleration, sorry. did I say air resistance? Figure out the acceleration each time. And so this one, he's got air resistance of 1,000 and weight of 1,000. So his air resistance is going to be the net force, which is just 0 divided by 100 kilograms. So that's just going to equal 0. Okay, so what did we talk about? When the acceleration is 0, he's reached terminal velocity. So he was falling out of the airplane. His air resistance was getting bigger and bigger. Eventually, it equaled his weight, and now he's falling at a constant speed. But then he pulls open his parachute and changes things. Okay, so then once you get the numbers, you go over and you work on these questions over here. So what I'm going to do is I'm going to break you up into groups and let you finish the numbers over on the right side and maybe start looking at these questions, and then we'll come back and we'll finish it up. Okay, so I'm going to give you guys, say, 8 minutes or so to play around with this. And so I'm just going to break you up into groups again, and so you can work on this. Okay, so let's see. We've got breakout rooms. Okay. And you'll probably be in the same ones as last time. I don't know if it's by alphabetical order, but it's by alphabetical order of your first name. So let's see. Breakout 6 just has 2 people, so I'll redistribute them. Okay. So Amelia can go up here, and Emily can go here. Okay. All right. So anyway, so take some time, start working on this. We'll come back and look at it. And of course, this is very similar to things you'll be doing for homework and the test. Oops, breakout room 2 needed some people. Oh, there they go. Okay, hello again. Okay, so let's see how you guys did on the numbers. And so let's look at the worksheet. Okay, so what did you get for D? What was the acceleration? Let's see. Okay, -2. Good job. Okay, and I've got to get captions. There we go. All right. Okay, so -2. Okay, and what about for E? -10. Good. And for F, 0 again. Okay, which is pretty cool. So they've reached terminal velocity again, really. Okay, so let's go look at the answers over here. So when Bronco's speed is the least, his acceleration is which one? So his speed is the least would be when he first starts out, right? So when he first starts out, his acceleration is actually, is it the least or the most? It's actually the most, yeah. Because he's falling without any air friction, because that has to build up. So it actually turns out to be the most. I know it seems like it should be the other way around, but it's the most. Okay, now, where does he experience a downward acceleration? And you can have more than one answer, right? So downward would be A and B. Good, that's right, just A and B, not C because it's a 0. Yeah. Okay, so he's downward acceleration. And then upward acceleration for part 3 is D and E. Okay, good. All right, so negatives would be showing an upward acceleration in this case. And that's because we initially, our velocity downward, we just assumed was a positive. So yeah, so negatives are upwards. Okay, when he experiences an upward acceleration, his velocity is still, which one? Still downward, right? So he was moving very fast downward, and now he's starting to slow down, but he doesn't go backwards. And so that's something when you see in movies, um, somebody pulls their parachute open and they seem to fly upwards. And what's happening is that you're forgetting that there's a person with a camera, and the camera person is still falling. And so they don't pull their parachute at the same time. So it looks, to your point of view, the camera point of view, that the person has suddenly gone upwards. And what they've done is they've started slowing down, but they don't shoot back upwards into the sky. But that is a problem because when we see in movies, it looks like that's what happens. Okay, when is Bronco's velocity constant? And again, we could have more than one answer. Oh, good job. C and F. Okay, so yeah, when you have no acceleration, like in C and F, then you must have constant speed, right? And then when is terminal velocity? And that's the same answer, right? C and F. And where is terminal velocity the greatest? Good job, Hannah. Yeah. Okay, so if you got C, you were right. Because the thing is, he was going really fast. Then he pulled his parachute and started to slow down. So the second terminal velocity must be much lower. Okay, so that would be C. And if Bronco was heavier, his terminal velocity would be greater, right? You got that? Okay, right. So just like we talked about. Okay, so yep. Okay, very good. Very, very good. Okay, so there is another side to this, which is on Newton's third law, which we haven't covered yet. So we're gonna go cover Newton's third law now, which has lots of cool examples. All right, so anyway, so we'll get back to this worksheet later. Okay. All right, so let's go look at, oops, whoa, look at all this fun stuff. Let's go back and look at this. Okay, so there's a little section in here called forces and interactions. So force is a push or a pull, and interactions occur between one thing and another. So when you push against a wall, you're interacting with that wall. I know it's kind of weird sounding, but that's the idea. Anytime you try to touch something, you're interacting with it. And you don't even have to touch, like magnets don't have to touch to interact, right? Because the magnetic field reaches out and touches the other magnet. Okay, so they don't even have to touch, but they can still interact. And people used to be pretty amazed by that. I mean, you've grown up playing with magnets, but people used to call that action at a distance. And Newton, the word action meant force, basically. Okay, so that's why Newton's third law of motion is called the law of action and reaction. The idea is when you have an object and it exerts a force on a second object, so you push on the wall, then what happens is that the second object exerts an equal and opposite force on the first. So you push on the wall, so the force of your hand on the wall, and maybe that's 10 newtons of force. Okay, so thing is the wall pushes back on you, on your hand. So the force of the wall on the hand. And that will be an equal amount. So one force is on the wall, the second force is on the hand. And so push on something like the table right now, right? Push on your table with your hand, and you feel that there's a force back on your hand, right? The harder you push, the more force there is on your hand, right? So you can just do it with two hands, right? Push one on the other. Well, there's always, the harder you try to push them, each hand feels a force. Okay, so anyway, so this is always, sometimes people don't understand this because in cartoons, usually they'll have a force from one thing, but not the force back on the other thing. And so like my son's friend punched a tree once because he was angry. Well, you punch a tree and the tree punches you back. So his hand was quite bruised. So yes, so there's always a force back on you. Okay, now Newton said it in this way. He said for every action, there is an opposite and equal reaction. And so this one is the modern language, and this is the Newton's language. And the reason that we had to say it in the modern language is that people get confused about the word reaction. For Newton, what he was saying was for every action, so you can put the word force in there if you want, because that's more what he was thinking, action like a force. There's an opposite and equal reaction. And what he meant was force back. Reaction was a force back. But people get confused because they think reaction is what follows. So you push on a Jenga tower blocks, you push on the tower and they fall over. Okay. So you would think maybe reaction was the blocks falling over, but that's not what Newton meant. He meant when you push on the blocks push back on your hand. And so he was not talking about what happens because of the force. He's talking about just that force back on the original object. Okay, so anyway, that's why the law has the nickname, the law of action and reaction. They're talking about the force and the force back. So when you push on something, so let's say you're playing tennis or racquetball, one force is the action force. So something is starting, okay? So you're playing with a racket, so you're trying to hit the ball. So there's the force of the racket on the ball. But if you ever hit a tennis ball, you know that after a while you can get pretty sore because the ball is basically hitting you. So people get tennis elbow and sore wrists and stuff because the ball pushes back on the racket, right? In physics, we tend to say there's no free lunch. You can't have one force without another force. And so the ball pushes back on the racket. And it's an equal amount of force. So the harder you hit the ball, the harder the ball hits back on you. And so that's why the people who are hitting really hard, you can end up being very sore afterwards because you've been pushed back. Now, so one force is the action force, the other force is the reaction force, the force back. They're co-pairs of a single interaction. So the interaction was the hitting the ball, but there are two forces involved. Neither force exists without the other. You can't just have one force. They're equal in strength. They are opposite in directions. So if you hit with 20 newtons, you get hit back with 20 newtons. And they act on the two different objects. Now, those forces are just parts of what's happening in the world of, in the world. So in the world of the racket and the world of the ball. So for the ball, that's the main force on it. So it experiences this big force of the force of the racket on the ball. Now there's also, of course, a force of gravity, right? And there's also some air friction. So there's gravity, it's weight pulling downwards. There's air resistance pushing backwards on it as the ball takes off, right? So the thing is, that force is just one of the forces on the ball, but it is probably the very largest one. So that ball goes accelerating away, and its acceleration is mostly due because air resistance will be slow to start with, right? And gravity would be pulling downward. So its acceleration in this direction would mostly be that force of the racket divided by its mass. Okay, now the racket also has forces on it. For the racket, it's now experiencing this backwards force. Okay, the force of the ball on the racket. But it also has this hand gripping it down here. And so that force is usually larger than the force of the racket. And so coaches talk about follow through. So the ball may be hitting your racket, but you don't let the racket bounce back. You're supposed to follow through by pushing with an even larger force, a force of follow through. And so your racket keeps moving and keeps pushing on that ball till the ball is, takes off. And so you complete your swing. So yeah, so the racket, that's just one of the forces on it. And in that case, it's not the biggest force, so that your racket doesn't go bouncing back. Okay, so anyway, so that's the idea, is these two forces we started out with are pair of forces, but they are in different objects. And they're not the only forces around in the world. And the racket has gravity on it too, right? So anyway, so they act on two different objects. What happens to the object afterwards depends on its net force. What is the net force on the racket? What is the net force on the ball? Okay, but Newton's third law, action forces, reaction forces. And so they're all around us all the time, and we use them all the time too. So like when our car moves, our tires push backwards on the road, force of the tire on the road. And therefore, the reaction force is force of the road on the tire. And that pushes our car forward. So that's why cars turn and push backwards on the road, so that the road will push forwards on the car. Same thing happens with a rocket. In a rocket, the fuel moves around the chamber. It can only go one way, backwards, right? So what happens is that the rocket, the sides of the rocket are pushing on the gas, and the gas molecules are in here bouncing around, pushing on the rocket. And so that direction, right, is forwards. So particles go backwards, rocket goes forward. And so same thing with Earth, okay, or exercise. You pull on a spring or a weight, the weight pulls back on you. And the Earth, when you drop something, well, there's the force of gravity pulling on the object. And amazingly, there's also a reaction force of the object pulling on the Earth. And so we don't really see this much because we definitely see objects fall, but the Earth is so large, has so much mass, and this is just one of the tiny little forces on it, that we don't see the Earth accelerate towards us. Okay, so as we drop a rock or a ball, you know, we might expect to see the Earth come up as the ball goes down, but we don't see that because the ball has a small mass. So it's easily accelerated by the force of gravity. But the Earth has a huge mass, and all around the world, people are dropping things. So it's not going to react to our little ball falling towards it. Now, it does react to the moon. So when the moon circles the Earth does actually get pulled in the direction of the moon a little bit. So as the moon orbits the Earth actually changes its orbit a little and does a little wobble. So the center of the Earth actually moves in a tiny little circle as it's being pulled towards the moon. And the same thing happens with our star, the sun, as the planets go around it. The sun pulls on the planets, and the planets pull on the sun, and the sun does a little bit of a shimmy in the sky. And this is actually one of the ways that when we look out into space, we can see where a star has planets, because we can see that it's doing a little wiggle in the sky, and that indicates that there are planets pulling on it. So anyway, so yes, so action forces, reaction forces. And this is just an amazing thing. Even Galileo had no idea. This was just a weird thing that Newton came up with that nobody else was really noticing. But Newton felt it was necessary to talk about it. So action force, reaction force. Now this law, as I said, gets misused all the time. So you'll see it in car ads and TV shows, and then you'll see it in politics. Sometimes they'll say for every action, there's an opposite and equal reaction. And usually they're talking about something that follows after. They're almost never talking about force back. Okay, so be careful. This is one that gets misused a lot. Okay, but it's all around us all the time. And so it's an equal and opposite force. So we can put a negative sign to indicate opposite force. But what happens when they have different masses? That makes the accelerations different. So here we've got a cannon and a cannonball over here. Okay, so what happens is that the cannon has a much bigger mass. So it has a big mass, whereas the cannonball has a smaller mass. But forces have to be the same. And so since force is mass times acceleration by Newton's second law, then to make these two sides equal, the accelerations have to be different. So if the cannon is 30 times greater mass, then the acceleration of the cannonball is going to be 30 times greater than the acceleration of the cannon. So equal forces, but different masses make different accelerations. And the greater the mass, then the less the acceleration is. But if you've ever gone to a Civil War reenactment, we used to go to those. My niece was a Civil War reenactor, and so she was a soldier She had long braid of blonde hair at that time down to her ankles almost. So she had really long braid, and they made her tuck it into her coat because they thought it didn't look very authentic to have this long braid of hair sticking out of her wool coat, which she was allergic to. Anyway, but she was a tough little Civil War reenactor for a while. So anyway, yes, they always have, they'll have a fencing, a cord, so people can't get behind the cannon, because that's what happens with cannons. The ball goes one way and the cannon goes the other way, but not as far. It's got more mass, and usually they'll have part of it that drags on the ground so that it can't go back very far. Okay, but you don't want to stand right behind the cannon. Okay, so the thing is that this difference in mass also applies to when you've got car crashes. And so when you have different sizes, like a little car hitting a bigger truck, same sort of thing happens. The force is actually the same, but the accelerations are different. And so this is why one of those things, though, that again is hard to see is equal forces, because what you see is the truck is pretty much fine and the car is smashed to a little bit. But what's happening there is it's because of the acceleration. The truck sort of slows down, okay? It doesn't have to suddenly make a change in its motion because it has a small acceleration. The car all of a sudden is trying to change direction. It's being pushed back the other way with a huge acceleration. This makes things fall off. This makes it get crushed. And so as pieces try to go one way and then the other way, and this is what causes severe injury in people too, right? So you get whiplash and inside the car. So yes, so what happens to the objects depends on their acceleration, but the forces are equal. Okay, let's see, it's 11:26. No. We just got this last little bit. Guess we should finish it. I wanted to talk about the lab, but let's see. Okay, so anyway, this last little bit in here is about systems and external forces. And so there's not really much you need to get from this, except the idea that you can have a system of objects. So this little dashed line represents a system of objects. And you're not going to get tested on this either. It just introduces a few phrases like external force and internal force that we'll need later. So here we've got the orange, and the orange and the cart make up a system of objects. So everything inside the box. But you can see that there's an external force. This force is going outside the system. And that will make the orange accelerate. So they're not showing us the reaction force in this picture. They're just showing us the one object with one force on it, or the two objects with one force. Okay, so now we're getting a bigger picture. And we've got an apple, and the apple is the thing that's pulling on the orange. So now they're showing us both forces. So the force of the apple on the orange, and then the force of the orange on the apple. Okay, so anyway, so that's the reaction force. Okay, however, the system is still moving forward, right? Those forces don't cancel. And that's something people get confused at too, because they look at this picture and they think, well, those forces are canceling. But they don't cancel because they're on the different objects. So the force on the orange makes it accelerate. The force on the apple, that would slow him down, except we got to think about his other forces. He's pushing on the floor, right? So there are other forces possible on this apple. And so, in fact, as he pushes on the floor pushes back on him. So he has another force on him, which is the force of the floor or the road. Let's call it the road. Force of the road on the apple. Okay, because he pushed backwards and made a force of apple on the road. Okay, So anyway, so he's got an extra force on him, so he keeps moving forward, and therefore he and the orange are both moving forward. Now, what if we put him in the box too? Okay, if we put him in the box and didn't allow any external forces, then we would just have internal forces. So they're inside the box here, inside the system. And that doesn't cause acceleration because of the system. Because what happens is the apple is pulling on the orange and the orange is pulling on the apple. And even if it's a rope and the apple is like pulling the rope, well, if he doesn't have any friction, any contact with his feet with the floor, if he can't push on the floor, then he's just going to slide towards the orange. And the orange is going to slide towards the apple. And they're going to end up somewhere in the center. And the whole system wouldn't have accelerated. They just would have slid towards each other. And the center of the system would stay the same. So internal forces can't cause accelerations. But external forces can. So think about if you're inside a car, and have you ever had to push a car? I used to have a car that was so old. Well, it was in bad shape, and it kept dying on me. Okay, so I knew that it would be difficult to start also. So I would always park it on a hill in the parking lot of the college where I was teaching, because I knew it was going to be trouble to get started. And so then I would have to push start it. So I'd sit in the car and I'd open the door and put one foot out and push the car so it would start rolling, and then it would start up. So anyway, so I got, but the thing is, I couldn't just sit in the car and push on the dashboard. All right. So you're in a car and you're like, well, I can just sit here in my seat and push on the dashboard. That's a force, right? That should make the car go. But it doesn't. Because as I would push on the dashboard, well, to do that, my bottom would push on the seat. And those two forces on the car would basically cancel out. So I would have to stick my foot out and push on the ground to get an external force to start that car moving. Okay, so which my new car, yeah, that I actually had a car die not too long ago that I had to push to get it out of the way of other cars. Same way. Okay, so anyway, so with no external forces, there's no acceleration of the system. You got to get out and push on the ground. So now you've got an external force. So if we include the ground in the system, now the apple can push on that external force, the ground. Okay, so anyway, so that's what this is just introducing, is the idea of external force and internal force and a system of objects. And we're not using it much, but if the word comes up later, at least you'll know what it's talking about. Okay, so that's the end of this chapter, basically. Newton's 3 laws. The law of inertia: objects stay at rest, or they move in a uniform speed in a straight line unless acted on by a non-zero net force. So the first one is talking about what happens when you are having a zero net force, right? At rest or uniform speed. So equilibrium, static equilibrium, dynamic equilibrium. The second law is what happens when things accelerate, when there's a net force. So see how these tie together, right? So then it tells you the acceleration is the net force divided by the mass. And finally, the third law, the law of action and reaction. Whenever one object exerts a force on a second object, the second object exerts that equal and opposite force back on the first. So, first law, what happens if the net force does equal 0? Second law, what happens if it doesn't equal 0? It'll accelerate. Third law, what happens? Where do you get the forces from? So, action and reaction. Okay, so third law is about forces also. Okay, so this is a quiz I sometimes give. Okay, so I'm not giving it as a quiz, But you might want to think about it because sometimes it shows up on the first test. Okay, so apply Newton's 3 laws to a golf club striking a golf ball. So, first law, right? The golf ball, if it was sitting still on its tee, would stay at rest, right? So things at rest stay at rest. Once it's been hit and it starts to move with a constant speed, then it would stay that speed till forces come along to change it, right? So gravity would change it, air resistance would change it. If it hits a tree, that's going to change its motion. But otherwise, that golf ball would continue moving forever at a constant speed. So you can talk about it, think about it at before it's been hit or after it's been hit. Now the second law, acceleration is the force divided by the mass, right? Acceleration is net force divided by the mass. So one thing is that, of course, the golf ball is applying a large force of the club on the ball. And so what happens is that that force is most of the force on the ball. So we'll just use that one. And so the ball is going to accelerate because it has a small mass and it's going to have a large acceleration. Right? Because the smaller the mass, the larger the acceleration. And the larger the force, right? The larger the acceleration. Remember that force and acceleration are directly proportional, but mass and acceleration are inversely proportional. So small mass of the ball, and then you get a large acceleration. However, also you might think about, well, the golf club has more than one force. It has a reaction force, the force of the club on the ball. So this relates to Newton's third law, right? And so the third law comes in there, in that you can think about what are the forces on the golf club. So there's the reaction force from the ball, but of course there's also, way up here, someone hanging on to this club. And so because of that, then what you have is another force on the club that keeps it driving forward. And that's that follow through again, that coaches love. They want you to keep a hold of that club and keep it moving, move it forward. Stay in contact with the ball as long as possible, so you give the greatest acceleration to the ball. But meanwhile, this force is bigger than the ball back on the club. Okay, so, and of course, the golf club has a bigger mass than the golf ball. So it receives less acceleration back from the force back on the ball, back on the club. Okay, so anyway, so you can combine these. You can see how the second law and the third law combine with each other, because the third law is action reaction. It's talking about forces. And the second law is about how much it accelerates when you get a force. Okay, so you might think about this because usually this problem is on the test. Okay, so it looks like we are pretty much done here. So let's go quickly back and look at the lab for a minute. So that's the end of the chapter. Okay. And, oh, let's look at the worksheet for a minute. So the other side of the worksheet is just filling in this sheet where you have these situations. And so in, like, when you've got here the bird's wings push downward, then you're supposed to say what the reaction force is. So the wings push air downward. So the air, so turn it around, air pushes wings upward. Right? So make sure that you get the reverse direction idea in there also. Okay, so two different objects, air and wings, And this is how a bird flies. They push downward on the air, and the air pushes them upward. It's kind of how airplanes work too. We'll talk about that at some point. Okay, and so anyway, there's a blank here where you're supposed to fill in your own example. Okay, but otherwise you just sort of reverse everything here. And so that's what the second side is about. Okay, so we still have a few minutes. So let's go look at lab. And so you filled in that part. And then we talked about this. You guys chose some variables. And then you were supposed to gather items from around your house. So this is something that you probably did on your own. So gather 20 small items from around your house. And then you sorted them into three different times using different variables. So then you're supposed to put pictures in. And so they can be pretty amusing. Let's see. I go back to, oops, not that one. No, that's not what I want. Why are you up here? Oh, that's why. Okay. Okay, if I go back to last year's class, let's see. So fall. Okay, and go to assignments. And down to labs. Oops, that's homework. Keep going down to labs. And let's see. Let's see what Brianna had. Yeah, she got all her points. Okay, so that was good. Oh, it's taking time. All right. So, anyway, so still thinking. Okay. So here are some objects that she had, and you can see she divided them up into piles, took a picture, and talked about how she was dividing them up. So this one was color. And then she divided them again by texture. Okay, and she's got a plastic spider. She's got a fingernail file. So just some junk from around her house. Okay, and then she divided them up by weight, which is pretty cool. Okay, so medium and heavy and light. Okay, so that's the idea. Is you just insert the picture and you say what you're dividing them up by. That's as simple as it is. Okay, so anyway, so make sure that you do that. And I guess we're going to talk about the rest of the lab on Wednesday. Does anybody have any questions about that then? And then, and then the other part, of course, is you are going to answer questions. Okay, so there's some stuff about Galileo. And then there's the ball drop. So you drop a ball, and then you get the drop height and the rebound height. And I guess we're going to have to talk more about that on Wednesday, but let's see. We've got 2 minutes left. So yeah, so it helps if you, the way you can do this is you can put a piece of paper on the wall and, and mark where you're going to drop the ball. And then hopefully be able to mark where the ball ends up. Okay, so that's one way to do it. You could also put a tape measure on the wall or have a meter stick if you've got one. Of course, the higher you can get, so like if you can have a piece of paper that goes up higher than 1 meter, that's good too. You want to measure in, well, she did it in inches. Usually we prefer centimeters, but it doesn't really matter for this experiment because a lot of people don't have meter sticks. So You may have a tape measure that's only in inches. That's fine. Okay. So you drop it, and then how high does it bounce? And it does help to have a second person, maybe the person who drops it, so that you can be looking to mark when the ball comes back up. And you can also just eyeball it. So there's so you can try to, if you've got a meter stick, you can try to eyeball where it comes back up. Most of you won't have an orange and white one. So you would say, okay, it bounces back up, so you've got to be watching it to see where it comes back up. And that's okay. This data doesn't have to be perfect. And so you want to gather that data, and you got to do it for 2 balls. So hopefully you have 2 balls. And if anybody doesn't have any balls at home, then we can try to figure out something else to gather data on. But you gather the data, and you're supposed to watch, there's a video in here. There's a YouTube video of a kid who was a high school student who was doing this for his high school class. So anyway, so where we're looking for something called the coefficient of restitution. Anyway, well, we're out of time today, but that's the plan. So go get your data, and then we can talk more about this next time. And you can see I'm a real tough grader here. Okay, so check. Okay, so they're answering the questions. All right, so good job. And here's, she put a picture in of her cat helping here. So that's her assistant. So she was marking paper, so she taped her paper to the wall. It looks like she also had a tape measure that she was using, or so anyway, to figure out how high things are. And so, yeah, you're supposed to take a picture and attach it. Okay, so anyway, so that's the sort of thing that we do in the lab. Due date for worksheet. Worksheets are any time, so you can turn them in later in the semester or now. There's really no due date. I often don't grade a lot of extra credit till later in the semester. So, yes, so you can turn those in anytime. Okay, but it's better to do it sooner before you forget about them. So, yeah. Okay, so stick around if you've got questions. So stick around for office hours. Otherwise, have a great day. And I'm turning off the recording.